recording. Okay. So a couple things before we get started with, I managed to track down not a copy, but something that's similar enough and has some of the questions that I really like on the final exam. Sorry, some of the questions I really like. I will send out an email for other stuff that I'll send out an email with regards to other stuff. But this final exam generally has stuff that I need. Let's see. Final exams on the 13th. I'll send out the day. No, this final exam will be all solo. Okay, just it's straight normal final exam. There's not going to be a group component to it, mainly because the reason for that is that we use the same final exam across all sections, and the other students don't do the group finals, or do group exams. So this is all by you. Yes, it will still be on Canvas. The biggest difference is that I have a disclaimer that the first 5 questions, you don't use your editor or IDE for that. Okay. And I'll put a reminder for that on the first 5 questions that these are just questions that we don't want you to run there, because they are simple questions that I can ask. And if you don't, and I can test you on. So like, we're just going to enforce that by, just walking around and making sure you don't use your editor and stuff like that. Is there a practice exam posted? No. What we're doing today is we're going over various different practice exams for data structures from different universities. This is how I've always done it. I found this to be a very effective method for doing so. It's part of the reason is because it gives us a kind of a taste of other final of other universities and stuff like that, as well as the kind of questions. And I specifically go over these because these are very similar to the questions I'd be asking. Okay. Make sense? Okay. There we go. I've pulled up the ones I would like to go over. Okay. When's the last day to demo? When are grades due? That's what it comes down to. So you can demo before and after the final. I'm fine with doing demos so long as, look, what it comes down to it is just try to get it demoed to me before the final exam. If you can't, right? Yes, it totally is still possible to demo the regex. Okay. So anyway, just please try to have your things submitted by the last day of class, because technically that's when I'm supposed to have a hard deadline for stuff due. Okay. And again, if disaster strikes, something happens, please let me know. Worst case scenario for if you've been participating in class, and your worst case scenario is that we just either, I proctor the final over the break and do a grade change for you, or we do it incomplete. It is super easy. Email's generally the better way to do it. Okay. Yeah, and yes, when it comes down to setting up a meeting, just send me an email to set up a meeting. Just say, hey, I am available this day, and I'll tell you what times are available that day. Or you can ask me when I'm available, or let me know your general availability and I'll pick a time. Just there's tons of ways to do it. It's no problem. I'm still a bit, let's say, gross at the moment. So, anyway, all righty then. And that's why we're doing this online. Okay. But hey, it's like awful outside, so. Okay. Let's go ahead. And I believe this is it. Yeah, this is it. All right, so this has some of the questions from the final I was looking for yesterday. Okay, some of this has basic questions because it's like I feel like it's one of those accelerated classes, but hey, it's got some of the questions that I wanted to ask. So with a poorly chosen hash function, it is possible to have a situation in which the search time of a hash table of n items goes to O of n, O of n factorial, O of n log n, O of n squared, or constant time. So ideally, so this is with a poorly chosen hash function. We don't want a poorly chosen hash function. So this can't be right because that's what we want to do with a good chosen hash function, right? O of n factorial, that seems a bit absurd, right? Because what does a poorly chosen hash function look like? Let's write one. H of x is equal to 0. That's my favorite bad hash function, okay? That means that basically everything collides with each other. So what does that mean for a hash table if everything collides with each other? In that case, I try to go into here, but if this space is taken, I try to go to the next space. But if that space is taken, I try to go to the next space, which that's taken. And I keep going for however many items are in there. If there's n items in there, I have to look at n spaces before I find one. That means that a poorly chosen hash function means that this is O of n, worst case scenario. Make sense to everybody? Let's see. Oh, excellent. It does have all the questions that I want. Okay. A binary tree is constructed of the nodes that are instances of the following classes. And we see here that basically depending on the course, right, and depending on who the professor is and at the institutions, we have different priorities. Like, for instance, a lot of the universities that practice exams you'll see don't use generics. It's fine. Just I find generics to be very, very valuable and very good at making sure things, you know, for you to properly use the built-in data structures without it yelling at you for an error. Okay, so we have a node that contains an int and a left right, so it's a binary tree. And we have this function called mystery that takes in a root. All right. It takes in a root. And right, okay, that's great. That's what I want. So we take in a root, okay? And if root.right is null, then we return it. Otherwise, this says mystery root.right, which means we recurse. Make sense? So if it's null, return this thing. If it's otherwise, call mystery on my rightmost node. Oh, sorry, on my right node. You consult 3 tech-savvy consultants, okay? And you get the following 3 opinions about what the method does when past the reference to the root node of a binary tree. So consultant 1, it says it returns the last node visited by an in-order traversal. Consultant 2 says it's the last node in a post-order traversal. And consultant 3 says it's the last node in a level order traversal. What the heck is level order? That's just another way of saying it is BFS, breadth first search. Okay. So we've got opinion 1, opinion 2, and opinion 3. Which of these opinions is correct, regardless of how the tree is set up? All right, let's go ahead and go back to the non-vanishing version for this. Okay, so the last node visited in an in-order traversal. Okay. So this method says, hey, what I'm going to do is this node, if it doesn't have a right node, I'm going to return this node. Otherwise, go to, call the right node, which would then say if it doesn't have a right node, it's going to it's going to return itself. If it does have a write node, it's going to return the call on its write node. So in other words, this is going to keep going right. This is going to keep going to the right until we get to the rightmost node, which is, let's say for sake of argument, this guy. Okay. So that node will return. So that node will return itself, which will be returned to him, which will return to him, which will return to him, which will return to him. So in other words, this returns the rightmost node in the tree. This returns the node all the way to the right on a binary search tree, which means that it returns effectively, if it's a binary search tree, it returns the largest item in the tree. Make sense to everybody? This function returns the largest item in the tree. So it returns the last node in an in-order traversal. Well, an in-order traversal, right? It goes through the items in a tree and it will return them in order, right? So if we got something like this, 5, 2, 1, 3, 7, 9, and 10 over here, this would do 1, 2, 3, 5, 7, 9, 10. It will give it to me in order, as it says on the 10, which means that 10 would be the last item, which means that 10 is the biggest item. So this function would return this. And it would return the biggest item, which is always the last node visited in an order traversal. So 1 is going to be correct no matter what. Okay, we know 1 is going to be correct no matter what. There's nothing we can create that will falsify that statement. Okay. No matter what, the biggest node is always going to be the rightmost node. And that's all. And the biggest node is always going to be returned by an order traversal. Post-order traversal, right? Post-order traversal says, hey, return the left. Return means left, then right, then myself, or the root. So if we start at the root, the very last thing that's going to be returned is the root. So in other words, in a post-order traversal, this is the last node returned by a post-order traversal, but our method returns this node. So we falsified this statement. So 2 is not correct. Okay. Make sense to everybody? Number 3, so it returns to the last node visited in a level order. Level order is breadth first search. That means we go level by level, left to right. So 1, 2, 3, 4, 5, 6, 7. Or let's go ahead and draw it out a bit better, right? We have this node, doop, doop, right? So in this example, level order traversal, this would be the last one returned. And this is also the rightmost node. So you'd think, okay, great. But you can't be satisfied with one example. Let's think about it for a second. What if I remove this node that we would normally return over here? What happens now? Well, level order traversal, the last node returned by it would be this node, but the last node returned by our mystery function would be this. So there's a mismatch there. So only 1. So A is the answer. Only 1 is correct. The opinion 1 is always correct. All right. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets, so it can be determined very quickly. Okay. Very quickly, whether or not a given license is in the database. Speed of response is very important. Level order's last node is going to be the last thing in the last row. So level order traversal, right? So So this is the last thing in level order traversal right now. This would be the last thing in, this node would be the last one in level order now. So here, that's the last one. That item's still the last one. And this guy's the last one in level order traversal now. And level orders is basically, is like you're reading, you know, starting from the top, left to right. Reading in English, that is. Okay. So speed, so let's go ahead. It says speed, very important. Efficient use of memory, also important, but not as important as speed of response. Make sense? So in other words, speed is super important. Memory is not as important, but if you've got a strategy that uses memory, that's better on memory, that's the one we're going to use. Okay. So which of the following data structures would be most appropriate for this task, which is that we want to check. So a police department wants to check a database of up to 1,800 license plate numbers to see if a person, and we want to very quickly determine if that person is in this database. Okay. So what data structure should we use to check to see if a person is in this database? Or what data structure should we use for that database? We've got 5 choices: a sorted linked list, 1,800, a sorted array with 1,800 entries, a balanced search tree, a hash table with using open addressing with 1,800 entries, and a hash table using open addressing with 3,600 entries. And I like that they changed this up from last time. Okay, they changed this up from when I last saw it, because they didn't have this one, and they used to have a different answer which said a hash table with 10,000 entries, which I thought was a very good question, but that subtlety can be lost sometimes. Okay, so first off, a sorted linked list. How long? So basically what we're asking for in like if we're going to use Python syntax, which is we're checking to see how long the in operation takes, or the contains. How long does it take? What is the runtime for our contains method? To see if something's in a linked list, you have to check every item starting from the beginning and going up to and possibly including the end. That takes O of n time. Not a great, so that's a fairly slow response. A sorted array, if we're using a sorted array, we can do binary search on a sorted array. Okay. Which means that it takes log of n time to find something in a sorted array. Okay. Right? A balanced search tree also takes O of log n to see if anything's in it. However, in this case, a balanced search tree is great when you need it, when it's unbounded. You don't know how many items you need or you don't need, because those references, your nodes and its pointers are going to take up extra space. Whereas you're using exactly as much space as you need here, right? So it's going to take O of n extra space. This is going to use constant amount of space, 1,800. Whereas this is going to use like 1,800 a couple of times, if that makes sense. The reason I put constant here is this literally needs no extra space, whereas this needs some amount of extra space. So right now, our sorted array is winning. Okay, but now we have hash tables, and hash tables, we say that that it has a runtime of constant. Although I like to put a big fat asterisk there. Honestly, that's not a big fat enough asterisk. Let's go ahead and put there we go. Big fat asterisk there with drawn in highlighter. Okay. What is that asterisk? That asterisk is that basically that we have to sacrifice memory in order to maintain that runtime. And we got to make sure there's not enough collisions, right? Notice that it says it's a hash table using open addressing with 1,800 entries and 3,600 entries, right? Open addressing means, again, that I've got an array, and if my space, and I'm going to basically take every item and hash it to go to a specific space. I'm going to basically look at every item, tell it to go to this particular index. And if your index is taken, then you're going to look for the next available one. You're going to look over to, you're going to keep looking for the next available one. However, you need to have some buffer space. So a hash table with open addressing using 1800 entries. Well, think of it like a parking deck. We are trying to store 1800 license plate numbers in 1800 spaces. How long does it take to store each one of them? And how long does it take to find each one of them? Well, the analogy I like to use is a parking deck, right? Suppose there's one space left in a parking deck, right? We have 1800 spaces in a parking deck. You're trying to park in it, and 1799 of them are taken. How long does it take to find that last open space? It takes forever to find that space. For freaking ever to find the last available space in the parking deck, right? And the same thing happens here. As our hash table fills up, we get more and more collisions, right? As the hash table gets beyond 50 and 75% full, collisions become radically more likely because there's more spaces that are filled than those that aren't. And then those collisions cause other collisions because you can create clumps. So yeah, even though it's a hash table, when you have as many things that need to be stored in a hash table as you do in if you're trying to store basically n things in your hash table and your capacity is n, you're going to have a bad time. It's going to be essentially a linear runtime. On the other hand, we're trying to store 1800 license plate numbers in 3600 spaces. It's like trying to park a car in a parking deck that's half empty. In this case, half empty is the optimistic point of view for us because it takes no time at all to find a space. In fact, there's a formula, if I'm recalling it correctly, which by Knuth, which I think is the expected amount of time it takes to find a hash table, this expected amount of lookups is equal to, I think, 1 plus 1 over 1 minus, let's see, right. I think 1 minus 1 over L, where, yeah, the expected number of lookups is equal to 1 minus 1 over C, where C is the number of, where C is your capacity. So in this case, and C is your capacity, or rather, sorry, your load factor, rather. Okay, the load factor in this case is 1/2. We're never going to be more than half filled. Okay. Okay, I think it's 1 minus, it's 1 minus the load factor, if I'm recalling correctly. So C, 1 minus load factor would be, so we would get 1/2 over here. And so 1 over 1 and 2, that becomes 2, which makes this 3. So it's our expected lookup time is 3, even though we've got that, thousands of spaces to go through. This is a formula that your textbook goes over, I believe. It's Knuth's. All right. We've done something like this. Nodes for a doubling linked list look like this. Next stores a reference to the next node, previous is to the previous. Below is a list of 3 nodes along with 2 reference variables, mid and end, that refer to specific nodes in the list. So we don't have a head or tail, we just have our mid and end, because this list is special. Which of the following is not the first node in the list? Okay, so mid.previous, that is a node in the list. That is the first node. End.previous, end.previous, that's that one. Mid.next. So mid.next, dot previous would be a null pointer exception. Why? Because so C, mid dot next goes to end, dot next goes to null, dot previous, trying to call dot previous on a null causes an error. So C is definitely that. Dot mid, dot next, dot previous, and then let's see, last one, end, dot previous, dot next, dot previous. So the answer is C, because that one goes out of bounds. Because we're looking for the one that is not that node. All right. Okay, which of the following implementations of a data dictionary of n items? So in other words, which of the could require O of n operations to search for an item? So what in the world does that mean? I know what it means, so let me translate. Because so a dictionary, if you're familiar with Python, is this, which is the same exact thing as a hash map, also called an associative array. Now, as I went over in our videos, a map in Java has two kind of implementations. You can create a hash map, and you can also create a tree map. Both are possible implementations of a map data structure. A dictionary is also a map. So in other words, it's asking which one of these can have a O of n runtime, at least in some case. So with a binary search, so in other words, which of these three items, because they can all be a data dictionary, they can all be used to implement a map, can hit O of n runtime. Now, we don't know about 2-3 trees, but that's okay. What I can tell you is that a 2-3 tree is a special type of tree that every node has either 2 nodes or 3 nodes. Okay. What's special about it is that it is a self-balancing tree, meaning it is always balanced. And if it's always balanced, that means that we know that the worst case runtime in a tree has to be O of log n. It's not going to be O of n if it's the self-balancing tree. So we know that 2 is not out there. Okay, makes sense to everybody, even though we haven't experienced 2-3 trees. They're covered in chapter 9. They're not on the exam, but I mean, this is a good question. So, 1, a binary search tree. Well, I think we've went over this in our practice exam. Worst case scenario, a binary search tree that doesn't self-balance can become essentially a linked list with extra steps, right? So that can take O of n time. And finally, as we just discussed, a hash table, if we don't keep the load factor low, we typically want to keep the load factor if we're using open addressing at 0.5 or 0.75, meaning somewhere between 50 to 75% full. In other words, we're wasting n or some amount of space. This can hit O of n time if we don't keep a high load factor. So the answer here is D. This is not something you have to worry about if you're actually using maps. Huffman trees aren't going to be on the final exam, so I'm just going to skip over it for right now. Okay. Oh, I like this question. The following array is to be sorted in ascending order. Okay. We want this to be sorted from least to greatest. What algorithm will cause the array to be ordered 52, 47, 25, 33, 15, 14, 74 at an intermediate stage in the sorting process? In other words, which of these algorithms will cause us to have this? Now, I don't think they're doing quicksort the way I actually, let's see. Well, quicksort, yeah, we'll get to that. Okay, bubble sort. Bubble sort, the way that works is that the largest item bubbles to the top each time. Okay, well, the largest item is 74. And it does end up to the end, but we notice that 52 is now at the beginning. In bubble sort, items always bubble to the top. Bigger items are never going to fall. all the way down there, right? So 52, so we have 47 over here, 52 over here. 42 and 57 are never going to cross in bubble sort. They're just not. So it's not going to be bubble sort. Heap sort, okay, let's see. Heap sort, so what we would do with heap sort is that we would, this is probably our answer. I'm almost certain that it's heap sort. So heap sort, what we would do here is that we would turn this into a max heap. Or sorry, a min heap. So no, a max heap. So what we would do is that we would basically do 25, 47. One thing that we want to do though here, so let's see. So if it's a max heap, this is bigger than 52 is bigger than these children. It's bigger than these children. And then these nodes are there. This actually works. Okay. I'm pretty sure this works. Why? So what we would do here is that we would heapify this. Okay. How does heapify work? We start out with 25, 47, 14, 33, 15, 74, 52, like that. Okay. And what we do is that we start from the back. Let's see if they're doing it the way they should. We would start from the back and push, and we would try pushing each node down. We can't push any of these bottom nodes down because it's at bedrock. So now we try pushing 14 down. 14 is smaller than both. Now, again, this is a max heap. So the biggest item, so the bigger the item, the more it's going to go to the top. So let's see. 14, push 14 down here and to get to swap with 74, 74, 14. Then we push down 47. Let's see. 47 would swap. Oh, nope. 47's in a perfectly good place. And now we try to pop, and then we would push down 25. So we would push down 25. 25 would swap with 74, 25. And then we would push down on 25 again. 52 and 25. So we would get 74, 47, 52, 33, 15, 14, 25, which looks fairly close, except we've got 74 up here. But what happens? Well, the first part, now we have the first, what happened here is the first step of the sorting in heap sort. What you do with heap sort is that the biggest item is at the top. So you move it to the back of the array, by essentially doing a removal operation. Let me go ahead and clean this up. So once we've turned it into a heap, it looks like this. 52. Okay. So we push down. Now you won't have to know heapify for the exam, but I mean, it's good to know about heap sort in general. Okay. Because there are algorithms we care about. And it's good to know that about it in case we decide to ask you questions about heap sort, but we're not going to ask you how to do heapify. Okay, so now we've got this. First part of the sorting process is remove 74 by putting it in the back most position and pretending it doesn't exist anymore. 74. And so now 25 is here. And so now we have to push down on 25. 25 swaps with 52. 52 becomes our new root. And now we pretend 74 doesn't exist. And now notice we've got 52, 47, 25, 33, 15, 14. So that would be heap sort. Now it's not the other ones. Insertion sort would be basically going to insertion sort. We'd expect a sorted subarray at the beginning. And we certainly don't have a sorted subarray at the beginning. Quick sort, we'd expect all those items to be less than the pivot and all the items to be greater than the pivot on each side. And selection sort should always have the smallest item at the front. Basically, the smallest items get moved to the front there. So it's got to be heap sort. It's actually fairly straightforward also then just knock out with, process of elimination. I don't know why I had trouble doing that those words. All right. Let's see. That's a question like we had on exam 2. Just trying to see. Topological sorting. Okay. That was just looking for a good one. Okay. Excellent. So we have this array here. It's going to be sorted in ascending order. After the initial pivot partition version being discussed in the lecture, with 36 being the pivot, how would the array be ordered? The issue is that in our partition step, what we would do is that we would select so the issue here is that they want to do quicksort a bit differently than we do. They say, okay, they want 36 here. So for the sake of argument, I want 36 over here because when we went in our algorithm, the basic version of quicksort says choose the leftmost thing as the if I'm going to ask you to do quicksort on the exam, it's going to be something along the lines, use the leftmost item as your initial pivot, right? Because that's the way it works. You use the leftmost item as your initial pivot. What you do is you start it out with the unsorted array. You choose your pivot. Sorry, you choose your pivot and you have this unsorted array. And then when you do partition, what you get is you get your partition, you get all the items less than the partition, then you get all the items greater than the partition, and then what you do is that you swap the partition with the last item in that leftmost space. And so you can get all the items less than the partition, and all the items greater than the partition. Make sense? Let's go ahead and walk through that. So how do we do this? So what we're going to do here is that we have 36, 53, 71, 62, 17, 46, 41, 23, 12. So first we create two variables, up and down. Up looks for the first thing that is greater than our pivot. This is our pivot. And down looks for the first thing that is smaller than our pivot. Okay, up. So we go up the array indexes, and we find that that 53 is is bigger than our pivot, and we go down and we find that 12 is smaller than our pivot. So we swap these two items. 12 and 53. Okay, and now we keep going. Up for the first item that we find that is bigger than our pivot, and down for the first item that is smaller than our pivot. 23 and 71 get swapped. Up for the first item that's bigger than our pivot. Wow, they really ordered. And then down for the first item that is smaller than our pivot. 62 and 17. Swap them. And that give me 1 second. Okay. So now, if you notice, we have our pivot. Sorry, now we do the same thing. We look up for the first item that's bigger than our pivot, and down for the item that's the first item that's smaller than our pivot. Up and down has crossed. If the value is equal to the pivot, either treat it as greater than or less than. One of the two. You can't just put it anywhere. You want to be consistent. Anyway, up and down have crossed. And because up and down have crossed, let's take a look at what's happened. We've got our pivot. We've got all the items that are less than our pivot and all the items that are greater than our pivot. So so these are less than 36, greater than 36. And now the last thing we want to do is that to finish partition, we swap with the last item in the less than section. So our final answer would be 17, 12, 23, 36, 62, 46, 41, 71, and 53. I typically, when I do these kind of things, I like to do single digit numbers because that's a lot less writing. Okay. So. Okay. First occurrence is the first list and the second list. Matt. No, thank you. Here we go. Trees. Those are add and remove things. Let's see. 2, 3 tree. Nah. Over here. This is a good question for us. Hashing. We're given an initially empty hash table of size 7 that uses open addressing. The following sequence of keys is to be inserted into the table, right? It's normally key value pairs, but we're just gonna only care about the keys here. Okay. Indicate these keys using each of the following approaches. If an overflow occurs, say so, and indicate the element that causes the overflow. H of X is equal to X mod 7 linear probing. So in other words, our hash function is take the key, mod it by 7, and that will be where we put it. And we use open addressing with linear probing to resolve. Linear probing means that we look for the next available space, where next is defined as literally add one and then add another one, then add another one. Quadratic probing means look 1 away from our initial spot, then look 2 squared away, then look 3 squared away from our initial spot. Okay, so let's do this in turn. So 15 mod 7 gives us 1, right? 15 divided by 7 gives us a remainder 1. So 15 is going to go into this spot. 17 mod 7 is going to leave us with the remainder 3. So 17 is going to go over here. 8 mod 7 is going to give us 1. So we're going to try to put 8 over here, but we can't. So instead, we're going to put it over here in this spot. 23 mod 7. 23 mod 7. 23 divided by 7 is, well, that's going to effectively give us, we're going to be able to take out 21, which leaves us with 2. So we have remainder 2. So 23 is going to try to go into this spot, but it can't. So it's going to try to go into this spot, but it can't because it's already taken. So 23 is going to try to go into this spot, which it can. So we put it over there. 3 mod 7 is 3. It's fairly straightforward. Well, 3 can't go here, and it can't go here. So it ends up in spot 5. 5 mod 7 tries to go into spot 5, and it can't, so it ends up in here. And that's how it's filled up. Now for quadratic probing, our initial steps look exactly the same, which is we put 15 mod 7 over here and 17 mod 7 goes over here, right? For 1 and 3 respectively. 8 mod 7 gives us 1. So we look 1 squared away from our initial spot. No problem. 23 now. 23 says, let's look at spot 2. 23 wants to go here. It can't. So it looks 1 squared away. from its spot. Can't go there. So now it's going to look not 1, not 2, but 4 away. That's 2 squared. So 1, 2, 3, 4. 1, 2, 3, 4 away from its initial spot, and it's going to go into here. Make sense? 3 will try to go into here. But it can't, so it goes into spot 4, and then 5 has no problem slotting in. Make sense to everybody? Okay. And double hashing is not something we covered, but that's fine. Okay. A few more in the way of theory, and then I'll cover another another question with regards to doing some coding. All right. Graph algorithms. Perform a depth first search on this graph shown above, starting at vertex C. So start here. And since we have options, since it could be done ambiguously, we're going to go ahead and say, hey, these edges have weights, so select the smallest edge first. And then the next problem says, do the same thing, but with breadth first search. All right, so select the smallest edge first. So C is going to go into, so in the space below, list the order in which everything is visited. So for depth first search, we start at C, we have a 5, a 23, and a 30. We're going to go with the edge for 5, which brings us to B. Now we're at B. So now we select the smallest edge that brings us to an unvisited spot. We have 18, we have 20, we have 17, and we have 13. 13 is our smallest one, so we go to A. A has 13 and 10. We have been to this one, so 10 is our only choice. So we go along the 10 edge to get to D. C bad so far. D is a dead end, so we backtrack. A is a dead end, so we backtrack to B. So now we're back at B. B has 2 unvisited edges, or edges that bring us to 2 unvisited neighbors, 18 and 20. 18 is the smallest edge of 18 and 20, so we go along 18 to F. F is a dead end. It doesn't bring us to any unvisited node, so we backtrack to B. B has 1 unvisited node, which is E. We go to E. E is a dead end. We backtrack. B is now a dead end. We backtrack. C is a dead end, so we backtrack. We're out of nodes to visit. We're done. So our answer is C bad phi. C B A D F E. C bad iron, or something like that. Now for breadth first search, doing the exact same thing. So what we do is that we start at C. So here we're going to actually need to write down what we're doing. So C, we've got we've got C, and we want to go to B. We see B, E, and F next. We want to go to B, and Q just stands for our Q. B is the smallest thing, so we want to smallest edge, so we want to go there first. E is the next smallest at 22, so we're going to go there next, and F is the next smallest. So DQ, we visit B. We're at B. We've got 5, but we've already been to C. We've got 18, but 18 is already in our queue. But F is already in our queue. 20, but E is already in our queue. 13 for A, and 17 to get us to D. So we add A and D to our queue. And now we go to E next. That's the next thing in our queue. And that gives us no extra information. Go to F next. That gives us no extra information. Then we go to A next, which gives us no extra information. and then we go to D next. What we did here effectively is that we went, so it's CBEF 80. CBEF 80. What effectively, again, we did here is that we started here at distance 0, then we went to distance, everything that was distance 1 away, and then we went to everything that was distance 2 away for breadth first search. Generally, if I give you if I ask you to do something with nodes, I'll ask you to break those ties alphabetically. Okay. So here we go, Dijkstra's algorithm. We want to figure out the distance from D to E. It doesn't matter from D to whatever, because we're going to have to figure out what everything is anyway. So we've got our nodes A, B, C, D, E. We've got our distances, which is going to be infinity, infinity, infinity. D is 0, and we got there from ourselves. And then E is infinity as well. And get there from D. So now we look at D's. We look at D's neighbors. That gives us D's neighbors are A and B, and they are connected by length 13 and 17 respectively. We're done populating our list with D. So let's look at A. Sorry. No, I misspent that's 10 and 17. 10. So we look for the node that has the cheapest distance. That's to A. So we look at A next. A has one node we haven't visited yet. There's one edge we haven't seen yet, which goes from A to B. So is 10 plus 13 a cheaper path than just going from D to B? No, it is not. So we don't update. Remember this one not being a particularly awesome graph for this. Okay, next we have 17 infinity, infinity. 17 wins. That's the cheapest thing. So now we've got, this gives us 3 new edges. One of a 5, one of an 18, and one of a 20. Okay, we know the cheapest way to get to there to B is 17. So is 17 plus 5 a cheaper way to get to C? Well, yes, it is, because it's better than infinity. Oh, I forgot to put down an F. I'll just put that down over here as well. Infinity and D. All right. So I'm going to be updating all these. So I'm going to go ahead and erase. So B to C. So B to C, 22 total is a cheaper path. So we put down 22 to here. 17 plus 18 is 35 for F. And then E, 20 plus 17, which is 37. Is cheaper yet. And then this ends the problem, because guess what? C doesn't provide us any better paths, nor does E, nor does F. So we effectively finish. Nope. Okay. Okay. Suppose you want to print out a binary search tree like this one in reverse level order. Ooh, that's a new one. So that the labels of the nodes of the tree in the diagram would appear in reverse alphabetical order. So in other words, if I did reverse level order on this algorithm, it would be it would be FEDCBA as our output. Says here, describe your pseudocode here. Okay, we can do better than that. So unlike other things here, this would be, honestly, I can just pretty much do that over here. Don't need the IDE. So what we do over here to do reverse level order is that we have our function. We have our function f, which takes in our node root, right? And all we do here is that basically we have this is breadth first search, but the output needs to be reversed. So instead, what we're going to do is that we'll have a Q output is equal to new, supposed to be a linked list, whatever, there. And then we're going to need, actually, no, that's our Q is not the output there. My bad. Our Q is equal to a new linked list. And if we were doing this normally, we wouldn't even have to have a stack. What I'm going to do is I'm going to use a stack to store our output, because as I put things into the stack, it will get reversed. New stack. Now all I have to do is thus Q dot add, Q dot, I think it's offer. I'll just use NQ here because it's pseudocode. NQEUE root. And then while Q is not empty. While Q is not empty, current is equal to Q dot pull DQ. So we get the thing in the front of the queue. And then we're going to do Q dot add, Q dot NQ. Current dot left. Same, but right. And then output dot add, or output dot push. Current. And then print output, which is our stack, which has now everything in our reverse order. Make sense? I know, chicken scratch, but I think we get the idea. It's fairly straightforward to do. Okay, that's adding to a linked list, blah. Search, so that uses iteration rather than recursion. I like this one over here. Write a Java method named mirror. Love this one. This one's great. But I didn't give it as a practice problem. If this wasn't a practice problem, I'd be asking something like it on the exam. It's beautiful. Write a method called mirror that takes in a reference to a root node, to the root node of a binary tree, and creates a new binary tree with its own nodes that is a mirror image of the original tree. For example, if root is a reference to the tree on the left, then the return value of mirror root would be the thing on the right. So instead, it's much easier if you use writing recursion. Oh boy, it is. So 1, 2, 3, 4, 5, 6, 7 would become 1, 3, 2, 5, 4, 7, 6. Now this one does seem like a bit of a tricky one to do. But worry not, it's actually not too bad. So okay. So let me go ahead and share my screen because I'm going to type this one up. Okay. Okay. New share. Okay, everybody sees the IDE now. Right, this is where we left off yesterday. So let's go ahead and write this function. Public. Public. Going to return a new reference. It's going to return a new node. Public. No, yeah, let's go ahead and public static. We're going to make it static just because it's easier for me to code without errors that way. Public static e node e, because otherwise I have to add in all the size and stuff for the data structure. Here I'm just dealing with a node. Public static e node e mirror. It takes in node, takes in the root of a node and produces its own mirror image and returns the mirror image of it. All right. So first off, return null to quash this error, to quash the errors. Oh, right. I got to give it a name, root. There we go. That's part of the reason I quash the errors, the return error, so that I can see if I've made any other errors. Okay. So first off, base cases, right? Base case is always the first thing to do. So what is a base case? Our base case in this case, a good one with trees is always checking if the root is equal to null. Right? If the root is equal to null, then what should I do? Well, if the root is equal to null, what's the mirror image of null? It would be null. So I would return. So I feel comfortable returning null here, actually. Else, or otherwise, we don't need the else. Otherwise, we need to create. We got to create a new node. Node e mirror root. It's equal to new node. Now, the reason we have to create a new one is because if I've got some node over here that is like this, L, R, then after I mirror it, I need a new node, a new root, which will have its own copy of R and its own copy of L swapped and mirrored as well. So new node. Let's see, root dot item. Yeah. What is wrong there? What is wrong there? Oh, make mirror not static. Make node static. Yeah, I guess. Fine. Make mirror not static. That's fine. Okay. Okay. Node e mirror root. So we created this mirror node. Node. So now what we need to do is that we need to do the left and right. Figuring out how to like swap everything around in my left tree and everything around in my right tree is hard. So I'll just use recursion to solve that. So I'll say mirror left is equal to the mirror of my left side is equal to well, actually, we can just do this a bit easier. So now that I've created a mirror root, I'm going to return, that's going to be my return value. Right? I got to return that copy. I want to return the root of a new tree that's been mirrored. So what should the left side be? Well, the left side should be my right side. Mirror root dot left is equal to root dot right. Except that's not enough. All that is just simply I'm just simply saying, hey, I've got this node and I've got this other node. So now I'm saying that this guy's left is equal to this. No, I need my own copy. And also, I want all of his children to be mirrored too. So I'm going to tell root's right node to mirror itself. And mirror root dot right is equal to mirror root dot left. So essentially what we do is I swap root's children, and then I tell root's children to swap their children, and so on and so forth, which is how the original one worked. And that's it, believe it or not. And this worked because, again, mirror returns a root. If one of my children is null, I'll get null. Sorry. And if right is null, I'll get null back for left, which is what we want, right? Let's go ahead and go back to the screen share. Right? These things swap. All right. Just fine. All right, what is the runtime for mirror? Use big O notation. It is O of n because we touch each node once. We copy each one, we address each node and make a copy of each node. Every node gets called by mirror once, and mirror does nothing too complicated on it. Okay. So with that, we have about 10 minutes left. So I've got a couple things to say before I dismiss you. So first off, I'm very proud of everybody who's made it this far and has been working on this. I'm not going to be working opening up breakout rooms for demos. I have another lecture that I need to prepare for today, and I need to give my throat a chance to rest because I'm still recovering. I kind of need to conserve my energy. I will be meeting with people throughout the break to demo. Okay, so throughout the final exam period, if you still have stuff to demo, that's perfectly fine. If you still need some help on stuff, I'll be available all weekend, as well. But again, I wanted to say I'm very proud of y'all for making it this far and for doing all this hard work. I know that this semester has been tough. You've been saying stuff. Apparently my volume's been turned all the way down. So so I know that so anyway, your next steps really do depend on what your major is. If you're in computer science, you'll most likely go to 3223. If you're IS&T, you get to not do that. So there's a lot of but this is at this point, once you've taken this final exam, don't be afraid to to apply for like big companies and stuff. Yes, there's all sorts of worries about recessions and jobs stuff right now. Don't let that deter you. Really don't. And furthermore, don't let that be an excuse for them to accept underpayment. You're worth money. How much money? Well, you can't buy more time, and you only have a finite amount of it, and you're trading your time for money. So the answer is you get as much as you can. So seriously, don't undersell yourself, and don't be afraid to, you know, go for a big shot. This class is one of the ones that is that, you know, that interview questions like to draw from. If you need some pointers on how to prepare for interviews, I'd be more than happy to help. If you need some pointers on how to do mock interviews, I'll drop a link in chat. Go to this website, pramp.com. That's like one of the best websites I've seen for this. It's a great website for doing this kind of, for doing mock interviews. So also, again, research is an option at this point if you want to pursue that or get interested in that. As far as recommendation letters, generally, if you get an A in this course, I'd be more than happy to write a recommendation letter if you need one at some point. Okay. So, let's see, other things. Now, I'm sure some of you are probably need more resources would like more resources and stuff for studying. I cover a few more things. Didn't get the chance to cover as much as I normally do, I feel, for these courses. So again, if you go to your data structures course over here and you go to lecture recordings, you know, I'll make sure to upload this, but go ahead and like scroll down to like the previous to some of the previous semesters, and you'll be able to find, you know, final exam reviews, and those will be generally helpful to you. Make sense? Those will be generally helpful. Okay, so any questions before I dismiss class? All right. The last thing I'll say is that please fill out your student feedback forms. We really do rely on that to know how to improve our classes. Especially I like reading mine and figuring out, and if you have complaints, that's also the place to put it. Again, those dues get read. So please take the chance to fill out your feedback forms for all your courses. Also, like the YouTube stuff, I keep it on YouTube for a reason. So you'll have access to it after the semester is over, you know, if you need to refer back to it. I don't plan on ever taking it down. And if I have to take it down, I'll plan on moving it somewhere else so where it's easy to access. Okay. I won't be able to stay behind right now, but I'd be happy to meet like tonight or this weekend. Okay. All right. Well, with that, class is dismissed. I will see you all for the final exam. I will send out an email with the time and date and place of that. Take care.